All right, today I'm going to show you some work and energy example problems. Problems that can be made possible or simpler using the work-energy theorem. Let's start with one that uses a non-conservative force, friction. So imagine I have a crate of oranges with a mass of 2.33 kilograms, and it's sliding across the surface with a coefficient of kinetic friction equal to 0.323. The crate slides 5.15 meters before coming to a stop. What was the initial velocity of the crate? How fast did it need to be moving initially in order to slide 1.15 meters before coming to a stop? Well, we'll use the snuggly dog method, and that starts with drawing a diagram. So here's my diagram. I have my crate with a mass m, and it's moving at some velocity v0, and then it slides a distance l before friction brings it to a stop. I've also got a free body diagram over here showing the different forces acting on the crate. There's the force of the earth on the crate. That's gravity. And that is countered by the normal force on the crate. And we know that they cancel because there's no acceleration in y, and those are the only forces with y components, okay? But then I also have the force due to friction on the crate. That's not Kentucky Fried Chicken. That's the force of kinetic friction on the crate, and that's in the negative x direction, slowing the crate down. Our objective is to find V0. And the givens are, we're given the coefficient of kinetic friction, we're given the distance it slides before stopping, and we're given the mass. And we can also assume that we know gravity, right, is 9.81 meters per second squared. Okay, what are our basic equations? Well, we can work this problem the hard way, and that's using constant acceleration, right? The force due to kinetic friction is a constant force, which causes a constant acceleration, so we can use our equations of constant acceleration, and it will work. But when we work it this way, and then go and work it using the work-energy theorem, we're going to see that work energy is a lot simpler. All right, but let's try it the hard way first. So first I'm going to, for my symbolic solution, I'm going to start with the x equation. And x minus x0, that's just the distance we traveled, which is L. So L is just equal to v0t plus 1/2 at squared. But the acceleration is just the net force divided by mass. And gravity and the normal force cancel out, so we just have this force in the negative x direction, which is the force due to kinetic friction on the crate. And so the acceleration is that force divided by m. But the force due to kinetic friction, of course, is just the coefficient of kinetic friction times the magnitude of the normal force. And we know the magnitude of the normal force because it just cancels gravity, and the force due to gravity is mg. So I'll replace that with mg, and we get this down here. And then the m's cancel out, and we get this equation, that the distance it travels before stopping is v0t minus mu kg over 2 times t squared. Well, great, this equation has v0 in it, but it also has t in it, which I don't know. I don't know how long it slides before coming to a stop. I need another equation. So I'm going to use the velocity equation, the constant acceleration velocity equation, and I know that my final velocity will be 0. It comes to a stop at the end. So I'm going to take my position equation, which gave me this, and then I'm going to take my velocity equation, which says the final velocity, which is 0, is v0 plus at. And once again, the acceleration is the force divided by the mass, which is the force of friction in the negative x direction. And the force due to friction is mu sub k times the normal force, and the normal force is mg. So here we have, of course, the masses cancel out, and we get this equation here. So now we have two equations, two unknowns. The unknowns are v0, which we want to find, and the time it takes to come to a stop. Well, I'm going to solve the second. So the way that we do two equations and two unknowns is we solve one of them for one of the unknowns and plug it into the other to get one equation, one unknown. I'm going to solve the second equation first because it's easier. And I'm going to solve it for t because what I want in the end is v0. So I don't want to eliminate v0. I want to eliminate t. So to solve this for t, first I'm going to move the mu sub kgt to the other side by subtracting it, or by adding mu sub kgt to both sides. Then I'm going to divide both sides by mu sub kg to get t. Then I can take t and plug it into the first equation, and I get L is equal to V naught times all of this stuff, which is T, minus mu kg over 2 times all of this stuff, which is T, squared. And if I simplify that, I actually just end up with V naught squared over 2 mu sub kg. So I basically have this equation right here. I just need to solve for V naught now. So I do that by multiplying both sides by the denominator, and I get V naught squared as 2 mu sub kgl. And then I take the square root of both sides. And there's my answer. Okay? So there it is. But now let's try doing this. So let's see. We had to do like a few pages of work to make this happen, right? So now let's try doing it the easier way, which is using the work-energy theorem. So, for the easy way, we're going to use the work-energy theorem. We're going to say the change in kinetic energy is equal to the net work done on the block. And of course, the kinetic energy is just 1/2 mv squared, and work is just the integral of force dotted into displacement. All right, so for my symbolic answer, I'm going to say, well, look, the change in kinetic energy is just the final kinetic energy minus the initial, but the final kinetic energy is 0. It comes to a stop, so the change in kinetic energy is just negative k initial, which is 1/2 m v naught squared. So there's delta k. Now let's find the net work. Well, there's only one force that does work. Gravity and the normal force are orthogonal to the displacement. Therefore, when you do the dot product in your work integral, you get 0. They do no work. So the only force which does work is the force due to friction. When we do our dot product, the force is in exactly the opposite direction from the displacement, and so we just get -1. The force, the magnitude of the force is constant, so it comes out of the integral, and then we just integrate dx from 0 to L, and we just get L. So the net work is negative force due to friction times L. And of course, the force due to friction is just mu sub k times the normal force, which is mg. So now we have the net force, and that should equal the change in kinetic energy, so we just equate those two. The change in kinetic energy is equal to the net work, and then we can divide by our m's, cancel out the minus signs, and multiply by 2, and there's V naught squared. Take the square root, and we get the same answer we did before. But look how little work we had to do. We just had to do a couple lines here, and then this. Much faster, much easier. Okay, now let's go ahead and plug numbers in. So we plug in the givens, and we find that the initial velocity had to be 5.71 meters per second to 3 significant digits. All right, do the units work? Well, we have the square root of meters per second squared times meters, which is the square root of meters squared per second squared, which is meters per second. Okay, so we get a velocity like we should. Gauge and guesstimate. Is this a reasonable value? Well, it must be going pretty fast to skid 5.15 meters with a coefficient of friction, which is like 1/3 of unity. But it shouldn't be going like the speed of sound or anything crazy like that, right? So 5.71 meters per second seems reasonable to me. No red flags, no alarm bells going off. So gauge and guesstimate does not give me a reason to doubt and think maybe I made a mistake. Let's look at limits, known cases, and trends. Well, if mu sub k gets bigger, that means more friction, so to go the same distance, it's going to have a bigger velocity. If g is bigger, the normal force will be bigger, and I'll get more friction, and to go the same distance, I'll have to have a bigger initial velocity. Or if it goes a larger distance, I'm going to need to have a bigger velocity. So if any of those go up, v naught should be bigger. And that's what our equation says, so that's good. All right? And if any of these are 0, v sub naught should be 0. If g is 0 or if mu sub k is 0, there's no friction force, right? If the coefficient of friction is 0 or the normal force is 0, it just glides with no friction. So it takes no velocity to go as far as I want. Or if L is 0, it takes no velocity to go no distance, no matter how big friction is. So if any of those are 0, v sub naught should be 0. And if I look at my equation, whoops, that's exactly what I get. And then our final step is in Snuggly Dog is, yes, I did the work myself. Okay. All right, let's do another problem. Let's consider a mass that's accelerated upward by a spring. A spring with a spring constant of 283 newtons per meter and a length of 10 centimeters is sitting on the floor. Then it is compressed to a length of 7 centimeters. A 200-gram mass is placed on the spring, and then the spring is released, launching the mass straight up. How high above the floor will the mass go? Well, I'm going to start off by drawing my diagram. So initially I've got this spring and it's compressed to a length L sub c. I've got a mass on it that's initially at a velocity of 0. My spring has a spring constant K. And then the spring pushes up on the mass. Oh, sorry. Let's do our forces as well. I'm kind of combining this diagram with a free body diagram. I've got the force due to gravity downwards, the force of the Earth on the mass. And then I have the force of the spring on the mass upward. Okay? And then the spring expands and pushes the mass upward, accelerates it upward, until the spring is completely uncompressed. All right? Then once the spring is completely relaxed, the mass continues to move free of the spring and goes up to a final height h. At this point, once it leaves the spring, there's only one force acting on it, and that is the force of gravity, the force of the Earth on the mass. Okay, so there's my diagram, and my objective is to find h, how high above the floor my mass will go. My givens are the spring constant, the compressed initial length of the spring, the uncompressed length of the spring, and the mass of the mass. Also, we can assume we know that g is 9.81 meters per second squared. Okay, so now what basic equations am I going to use? Well, I can try doing this the hard way, using F equals ma, and knowing that the force of a spring is negative kx, and that the force of gravity is negative mg. So, to do my symbolic equation, I'm like, okay, first let's find the velocity that it leaves the spring with. So the velocity once the spring is relaxed, it's not compressed anymore. Well, I can get a velocity by integrating acceleration with respect to time. And I'm going to integrate from time t equals 0 till time t when the mass is at the top of the uncompressed spring. Well, acceleration is just force divided by mass, right, according to Newton's second law. So that's just going to be 1 over m times the spring force plus gravity, the force due to gravity. But the spring force is just k times how much it's compressed. It's uncompressed length minus the compressed length, which is y, at any given moment in time. So at any given moment in time, the amount the spring is compressed is L naught minus y. And that force is in the upward direction, so we'll call that a positive force. But then gravity's in the downward direction. So we've got to do this integral, and things are starting to look messy because we don't know y as a function of time, right? We don't even know how long it takes to get to the top of the spring. So this is looking really hard. So let's not go any further. Let's abandon the hard way right now, and let's do the better way, the easier way, using the work-energy theorem. So for the work-energy theorem, our basic equations are the work-energy theorem, which says the change in kinetic energy is equal to the net work done on the object. And of course, work is just the integral of force dotted into displacement. Kinetic energy is 1/2 mv squared, and the force that a spring generates is negative kx. All right, so for a symbolic solution, I just need to find the work done, the net work done, and equate that to the change in kinetic energy. So first let's find the work done by the spring. The force from the spring is negative kx dx, and we're going to go from x equals, well, how far is x? X is how much the spring is compressed. So initially, the spring is compressed at amount L naught minus L compressed. That's how far it's squished from equilibrium. And then we're going to integrate up to the spring is not compressed anymore. X is 0. Okay? And of course, k comes out. And then we just have the integral of x. The integral of x is 1/2 x squared. So we do the integral, we get negative 1/2 kx squared, evaluated from x equals L naught minus LC to 0. Plugging those limits in, when we plug in 0 to our x squared, this whole thing becomes 0, and we're just left with 1/2 k L naught minus LC squared. So that's the work done by the spring. Now we need to find the work done by gravity. Well, the work done by gravity is just force dy, and the force is negative mg. And gravity is going to act on the block as it moves from a height of LC, the initial height, all the way up to the final height h. All right? So negative mg is a constant, so that comes out, and it's just the integral of dy. And the integral of dy is just y, evaluated between LC and h, is just going to be negative mg times h minus LC. So the net work is the work done by the spring plus the work done by gravity, which is this. The spring does positive work, gravity does negative work. All right? Now, we need to equate the net work to the change in kinetic energy. So what is the change in kinetic energy? Well, initially we're sitting motionless with the spring compressed, and at the end the mass has reached the maximum height, at which point its velocity is zero again. So velocity is zero at the beginning, velocity zero at the end, which means the kinetic energy is zero at the beginning and the end, so the change in kinetic energy is zero. So our equation then is that the net work is equal to the change in kinetic energy, which is zero. So zero is equal to the net work, which is this what we found before. And all we have to do now is solve this for h. So here's that equation. To solve it for h, first I'm going to multiply out this parentheses. And then I'm going to add mgh to both sides to move the mgh to the other side. Okay? And then I just have to divide both sides by mg, and I get h. So we took a problem which was impossible with what we knew, and using the work energy theorem, we made it actually pretty simple. So there's our answer. Let's plug in numbers now. So I plug in my givens into my calculator, and I get 0.135 meters, or 13.5 centimeters. The units, well, my units are newtons per meter divided by kilograms, meters per second squared, all times meters squared, plus meters. Well, kilograms, meters per second squared is just a newton, so that'll cancel the newton on the top, but I'm just left with 1 over meters times meter squared, and the 1 over meters cancels one of the meters and the meter squared, so we just have meters plus meters, which is meters. So the units work out. We were supposed to get a height, and meters are the right units. Gauge and guesstimate, well, it's a few centimeters. It's not millimeters, it's not kilometers, so probably seems reasonable. There's no reason for me to suspect that I did something wrong just based on the answer that I got. Let's look at limits, trends, and known cases. So here's my equation, and if I increase g or m, that should decrease h, right? The spring's only doing so much work on this thing, and it's trying to overcome gravity and mass. So is that what my equation says? Yes, if I increase m or g, the height goes down. If I increase the spring constant, then the spring's going to push harder, and that should increase h. Is that what my equation says? Yes, if I increase k, I increase h. If the compressed length is the same as the relaxed length, that means my spring is not compressed at all, and my mass isn't going to go anywhere. And my equation, in fact, says that h is equal to where I started from, LC, if those two are equal. If I increase L naught, that means I've compressed my spring more. I should go higher. And in fact, that's what my equation says. So it looks like I did a good job with this one. Let's work one more example problem. And in this problem, what we're going to do is we're going to figure out how many G's you pull when you swing on a swing. All right, so you're on the swing, up at some highest angle you're not moving, and then you come down, and if you've ever been on a swing, you know as you hit the bottom, you feel kind of sucked into the seat. So we want to know what our acceleration is at the bottom. How many G's do we pull when we go to the bottom? Okay, so here's my diagram. Swings go in parts of circles, right? So I draw a big circle. From the center of the circle out to my swing, that's the chain, and at any given moment, the chain will make an angle theta relative to vertical. Now, the forces on my swing are first the force of tension from the chain on the swing, and then there's the force of the earth on the swing. There's gravity, okay? My objective is to find the acceleration when I get to the bottom. Now, my givens are, let's assume I know the initial angle where my kinetic energy is 0, where my velocity is 0, and then I swing down. Let's assume I know the length of the chain, L, and let's assume we know gravity, the acceleration due to gravity. Okay, once again, there's a hard way and an easy way to work this problem. The hard way is to just say, well, look, the acceleration at the bottom is going to be inward, right? So the force due to tension and the force due to gravity will both be in the y direction when we're at the bottom. So there will be no tangential acceleration, only centripetal acceleration. And we know that for something moving in a circle, the centripetal acceleration is just v squared over r. And of course, we know Newton's second law, force equals mass times acceleration. So if we can find the velocity when we're at the bottom, r is just the length of the chain, L, then we can find that acceleration. Well, For my symbolic solution, I'm going to say, well, velocity is the integral of acceleration with respect to time. And acceleration is force divided by mass. And the force is going to be, the 1 over mass comes out, and then the force is the force of the tension on the swing plus the force of the earth on the spring, and blah, blah, blah. This is looking ugly. We're kind of reaching the same problems we had with the spring, maybe worse. So let's give up on the hard way, and let's use the work-energy theorem. So for the work-energy theorem, my basic equations are, I'm still going to use that the centripetal acceleration is v squared over r. And then we've got the work-energy theorem, that the change in kinetic energy is equal to the net work. And of course, work is just the integral of F dot ds, and kinetic energy is 1/2 mv squared. So the first thing we need to do is find the work that is done as it goes from its initial position, where it's not moving, as it goes down to theta equals 0. So the work due to gravity is just the force due to gravity dotted into a little displacement as I go from the top of my flight down to the bottom of the swing, right? Well, the displacement is in the direction of the yellow vector, okay? And so when I do my dot product, I just get the magnitude of gravity times the magnitude of ds times the angle between those two vectors, all right? But if I draw another arrow here to make a triangle, such that I have a right triangle, if you think about it, you can convince yourself that this lower angle here is theta. So phi must be 90 minus theta. So cosine of 90 minus theta is the same as sine of theta. So this is the integral I'm going to do to find the work that's done. All right, now notice though, so here's the integral from the previous page. I've just brought it forward. The magnitude of the force due to gravity is just mg, so we plug that in there. But theta is changing as we integrate, so I need to write like theta in terms of s or s in terms of theta. Well, a little piece of arc, when I change theta by a little bit, is just equal to the radius times d theta, right? So ds is just the radius, which is L times d theta. However, if we look back at this diagram, the work is positive, but theta is getting smaller, right? So ds is positive, but d theta is negative. So we actually need to put a minus sign in front of here. So ds is the same as negative L d theta. So I can plug that into my integral now, and I'm going to bring out the negative mg, and then I just have sine of L d theta. I can pull out the L as well, and I'm going to integrate from my initial angle, theta naught, to 0 when I get to the bottom of the swing. So I pull out the L, and then it's just the integral of sine theta. The integral of sine theta is cosine, negative cosine, so it cancels the negative, and then I evaluate that from theta naught to 0. And so I get mgl cosine of 0, which is 1, minus cosine of theta naught. Okay? Now that's my work. How much work is done by the tension, by the chain? Well, the displacement is orthogonal to the tension. So when I do the dot product in my work integral, I get 0. So the work done by tension is 0. So the net work is just the work done by gravity. Okay, so the net work is just the work done by gravity, which is mgl 1 minus cosine of theta, and that's equal to the change in kinetic energy. Well, the change in kinetic energy is k final minus k initial, right? But k initial is 0, right? When I let go of the swing, there's no velocity, so no kinetic energy. And the final kinetic energy is just 1/2 mv squared, where v is the velocity at the bottom when theta is equal to 0. So great, now I've got an equation I can solve to find the velocity at the bottom. I'll start by, canceling out the m's, dividing both sides by m, and then I'll multiply both sides by 2, and I get an equation for v squared. Now I don't need to take the square root, because remember, what we're after is the acceleration at the bottom, which is just v squared over L. So I just need v squared. So if I take v squared and divide by L, I get 2g 1 minus cosine of theta, and there is my answer. Numerical. So there's my answer. I didn't really give you any numbers, but let's just say what happens if theta naught is 90 degrees. If we're swinging all the way out to 90 degrees, what acceleration do you get at the bottom? So it's 2g times 1 minus cosine of 90 degrees, and cosine of 90 degrees is 0, so just 2g. So the acceleration at the bottom, if I start at 90 degrees, will be 2g. That's my actual acceleration, right? When I'm sitting on the swing and not accelerating, I feel gravity pulling me into the seat with 1g. But then I'm actually being accelerated up by 2g, so you would feel 3g's, right, on the swing. So because you're accelerating upward at 2g's, you would feel yourself being pulled into the seat as if gravity was 3 times what it is. All right? Okay. Now I can actually plug in g if I want to get a number for this. And to 3 significant digits, that's 19.6 meters per second squared. Units, well, my acceleration is equal to something without units times g, which has units of acceleration, so I'm good. Gauge and guesstimate. Well, it should be, it should be bigger than g, but not by much, right? It shouldn't be like 4, 5, or 6 g's, because people don't black out on swings. So I don't see any reason why I should suspect my answer based on the numerical values that we get, okay? Limits known, cases, and trends. Well, if I increase g, that should increase the acceleration, and that's what my equation says. If I increase theta naught, I go to a bigger angle, that should increase acceleration, and it does, just as I expect. My equation does not depend on L. Does that bother anyone? Well, it's not because we did it wrong, it really doesn't depend on L. So if you have a really long swing, you don't get any more acceleration than you would with a shorter swing going up to the same angle. So what is it that makes long swings funner? Well, first of all, you're up higher, so it's scarier, all right? Also, even though the acceleration that you feel isn't any bigger than you would get on a smaller swing, that arc is longer. You spend more time with, near the bottom where that acceleration is the biggest. All right? So that's the end of our example problems. I hope they were useful for you.